Landscapes, especially craggy ones like these, may appear solid and permanent. But geologists have long realized that the great leveling processes of weathering and erosion have caused many dramatic changes in the landscape. More recently, the dynamics of the complementary process, mountain building, have begun to be understood through studies of plate convergence zones. Indeed, many different types of relative motion between the rigid lithospheric plates have been discovered. This ancient stone circle lies in the northwest corner of the Eurasian continent, part of the Eurasian plate. Since it was built nearly 5,000 years ago, Castlereagh in the Lake District of northern England, together with the whole of Western Europe, has travelled about 90 metres in an easterly direction relative to North America. The lithospheric plates must be moved over the Earth's surface by a system of horizontal forces, forces which are generated by movements within the deeper, low-viscosity parts of the Earth's mantle. In turn, these convective movements are caused by the escape of heat from inside the Earth. The Earth's heat production and dissipation is one of the most speculative parts of Earth science, so later we'll look at the type of convection currents which might be occurring in the mantle. But although movement of the plates is part of the convective cycle, we do not observe large-scale convection within the lithosphere. Much of our knowledge comes from the observation of conductive heat flow and heat production at the Earth's surface. In continental regions, we can measure these quantities from boreholes. So we'll start by looking at the surrounding geology and then at heat flow data from a borehole in the Skiddaw granite, which was drilled to assess the geothermal potential of the area. Well, these are the oldest rocks in the Lake District. They're the Skiddaw slates. They're a fine-grained black slaty material that was originally laid down as a mudstone, but then became regionally metamorphosed by high pressures as the Lake District itself was folded up. These rocks can turn into something quite different, though, if they're affected by high temperatures. Well, I've been following the Skiddaw slates 3 or 4 kilometres northwest up the stream from the slate quarry we started at earlier. And I've been noticing that the rock's been getting rather harder, more crystalline and generally less cleaved. Now just take a look at this. This is called hornfells, and it's only produced in a zone of contact metamorphism around a hot igneous intrusion. What happens is that you get solid-state recrystallization of minerals into light and dark bands, and that's not the only thing that happens. The immense heat of the incoming igneous intrusion actually makes this hornfels plastic, so it can deform. See how contorted the bands become. Now, the source of the heat, the igneous intrusion, is the Skiddaw granite, and it's not far upstream from here. For all these boulders here are Skiddaw granite, and the granite here is sitting underneath the hornfells. I've collected this typical piece of Skiddaw granite. As you can see, it's not just any old granite, it's quite heavily altered. The only fresh mineral in here is the grey glassy quartz. Most of the felspar is altered to silvery mica, and the green mineral that you can see is chlorite, which grew from biotite. So originally, 400 million years ago, this was a fresh biotite granite. Well, we've followed upstream a couple kilometres more from the last outcrop of granite, and most of the way I've been crossing hornfells again. Now, hornfells is outcropping just down here behind me, and in this outcrop we can see some quite large needles of the contact metamorphic mineral andalusite, which grows at high temperatures. But even further back, where the little waterfall is, the granite starts again. So we've got rapid repetition of granite, hornfells, granite up the stream. And what this indicates is that the hornfells is lying on top of the granite as a very thin skin. So these intermittent outcrops of granite, then, are part of a much larger, massive batholith of granite, which underlies the whole of the Lake District. And it's this granite at depth which is still giving rise to heat today. The question is how much heat? To determine heat production, we need core samples, and to find the value of heat flow, we need to determine two quantities, thermal conductivity and the temperature gradient in a borehole. This hole is planned to go to a depth of 300 metres and is part of a Department of Energy project. By comparison of heat generation and heat flow values from this and other holes, we'll be able to build up a geothermal picture of first the Lake District and then of Britain in general. To select a drilling site, we need more information about the subsurface form of the granite, and we can get this from a gravity survey of the area. Underlying granite batholiths will show up as areas of negative Bouguer anomaly values on this map. If we look in detail at the gravity readings around Skiddaw, it's possible to calculate the extent of the Skiddaw granite quite accurately. The negative gravity anomalies are centred between Skiddaw and Carrick Fell, and this indicates that the granite is shallow and most extensive in this area. So geological fieldwork and geophysical data were used to select a site for drilling. Further fieldwork found that the granite cropped out as predicted in stream beds, here and here. The granite is clearly visible, and what is more, it looks fairly fresh, important because what we're looking for in the borehole is unaltered rock for laboratory studies. Unfortunately, drilling rigs are quite large and boreholes are, for preference, drilled on dry ground. An access road was necessary, as well as a patch of flat, firm ground on which to stand the rig and ancillary equipment. These geological and field requirements were all met in this position, centrally placed between the outcrops and overlooking the River Coldew. Drilling with a diamond bit began on the 24th of February 1982 and took a total of 11 days to go down 300 metres. Some rock core was required for laboratory studies, but because this is costly to produce, only 6 metres of core were taken for every 100 metres drilled. And for the most part, the cheaper method of hammer drilling was used to powder the rock in situ, the finely ground rock being recovered from the hole as drill chips. These samples illustrate the two different types of granite core which came from the borehole. At the top, fresh biotite granite, and below altered granite of the kind we saw earlier in the stream. The fresh granite contains 3 principal minerals: grey quartz, white felspar and black biotite mica. Only quartz remains unchanged in the most altered samples. The felspars, which have started to break down to secondary micas and clay minerals, are pink or green in colour, and the biotite has gone completely. Remember, these samples are from a borehole, actually from nearly 100 metres depth, so the alteration cannot be due to weathering. In fact, these changes have been caused by post-magmatic hydrothermal fluids that permeated through fractures. Fractures like this one, now filled with secondary calcite. On a microscopic scale, we find tiny grains of exotic minerals such as apatite and zircon, enclosed by fresh biotite crystals. The dark halos are radiation damage caused by natural fission of uranium and thorium, elements which must be concentrated in these tiny grains. As biotite has broken down in the altered granite samples, uranium and thorium will have been removed by the hydrothermal fluids, so we must measure heat production from the concentrations of uranium, thorium and potassium in the fresh, unaltered biotite granite. For chemical analysis, samples are crushed and milled in 2 stages to generate a powder. This process ensures that a small sample is representative of the whole rock. Batches of powder are melted in platinum crucibles and the melt is poured into a mould and pressed. On cooling, this leaves a thin, uniform disc of glass. Glass discs produced in this way from different parts of the Skiddaw core were analysed in the OU labs for a wide range of chemical elements using an X-ray fluorescence spectrometer. The average concentrations of long-lived radioisotopes of uranium, thorium and potassium were used to calculate the value of heat production for the Skiddaw granite, which is 3.5 microwatts per cubic metre. So much for heat production in the granite. What about conductive heat flow? Well, by running a thermistor probe down the borehole, we can establish temperature gradient. Here, the data from Skiddaw are plotted with depth along the x-axis and temperature up the y-axis. But to calculate heat flow, we need not just the temperature gradient, but also the thermal conductivity of the granite. They are related by this equation. From the graph, we already have a value for delta T over Z, which is 0.033 degrees per metre. To determine K, the thermal conductivity, is a detailed laboratory procedure. Here in the Imperial College laboratories, a disc of granite cut from the Skiddaw core is being saturated with water. It's important to displace air from the microfractures in the granite before measuring thermal conductivity, so that the natural ground conditions of water saturation are simulated. The disc is coated with glycerin to ensure that a good thermal contact will be made between the rock and the brass jaws of the divided bar apparatus. With the rock in position, the jaws are screwed up, and a temperature gradient is established across the brass-rock-brass column. Thermostatically controlled water baths maintain temperatures of 19 and 29 degrees centigrade at bottom and top of the column. At equilibrium, the heat flow through the rock, disc and brass will be identical, so the next stage in determining thermal conductivity is to measure temperature using thermocouples at intervals along the column. Thermocouples attached to top and bottom of the rock sample measure the temperature difference T2 minus T1 across it. If we divide this by the thickness, y, we get a value for the temperature gradient across the rock disc. This can be compared with the temperature gradient along one of the brass bars either end of the sample. The heat flow through both the brass and the granite is the same, so by comparing our two temperature gradients and knowing the thermal conductivity of brass, we can then calculate the thermal conductivity of the sample. This turns out to be 3.5 watts per metre per degree, and so we can now substitute it into our original equation to obtain a value for Q, the heat flow. That is 115 milliwatts per square metre, which needs to be reduced slightly due to topographic effects around the drill site. So now we have values of heat flow and heat generation for the Skiddaw granite.
What I'm going to try and do now is to use the relationship between heat flow, that's Q, and heat generation A, to interpret the source of heat below the Lake District. Well, we know that within certain continental areas, where both heat flow and heat generation have been measured in a number of boreholes, the higher the heat flow, the higher the heat generation. Well, this is obviously known as the heat flow, heat generation relationship, and it's expressed in this equation. That's Q equals BA plus Q star, where Q star represents the heat from the lower crust and mantle, and we can interpret B as the thickness of a layer of crust with heat generation A. Well, suppose we plot this as a graph of Q against A. Well, we obviously get a straight line. Therefore, if there's no heat from the lower crust, then Q is equal to BA. This term is 0, so all the heat that's measured is coming from the continental crust. On the other hand, if the rocks don't generate any radiogenic heat, then Q is equal to Q star, and all of the heat is from great depth. Well, measurements of heat flow, Q, and heat generation, A, from boreholes within a relatively small continental region give results that lie between these two extremes. And so a plot of Q against A gives a straight line on which Q star is the intercept of the line on the Q axis, and B corresponds to the slope of the line. Well, let's look at some actual data. Here's a plot of Q against A for drill holes from all over Britain. You can see that most of the values of Q lie between about 40 and 120 milliwatts per square metre, and similarly A ranges quite a bit between about 1 and 6 microwatts per cubic metre. Overall, the points show quite a lot of scatter, but if we draw a line through this data, it gives an intercept value of about 27 milliwatts per square metre. Now, if the mean heat flow from these data lies somewhere in the middle at a value of about 90 milliwatts per square metre, then comparing Q star with this value indicates that overall perhaps this third of the British heat flow is coming from great depth. Now, the slope of the line, that's B, corresponds to a thickness of about 17 kilometres. And if we assume that the crust has an average thickness of about 35 kilometres, then comparing the value of B, that's the 17 kilometres, to this thickness indicates that the contribution from radioactive heat producing elements is concentrated in the top half of the continental crust. Well, what about Skiddaw? That actually plots just here. It's obviously above the line I've drawn, but if you look at all of the scatter again, then maybe the idea of a single line passing through all of this data doesn't really mean very much. Well, in fact, these points are taken from boreholes all over the British Isles. And we've got very good geological evidence that the continental crust below Scotland is very ancient. In fact, the oldest rocks in Britain are the Lewisian gneisses, which occur in the north of Scotland and which are nearly 3,000 million years old in age. Below England and Wales, the crust is probably younger, and it's less than 1,000 million years in age. And further south, particularly in Cornwall, it might be much younger still. Well, let's look again at the data in terms of the existence of these crustal provinces. Perhaps we might be able to reinterpret the heat flow, heat generation data. Well, some of the Scottish points actually plot towards the bottom of this scatter, so they might lie on a line with a lower slope, indicating radioactive heat production from a relatively thin upper crustal layer, maybe 5 to 10 kilometres in thickness, that overlies ancient Lewisian crust with a low concentration of heat-producing elements. On the other hand, the QA data for England and Wales, and that's including Skiddaw, seem to fall on a steeper line. And this might indicate radioactive heat production from a thicker layer, maybe 10 to 20 kilometres in thickness, in which case it would form up to half the thickness of the continental crust. So we can try and use geology or geological knowledge of the structure of Britain to refine the QA data. And in doing that, the heat flow data has actually helped us to understand more about the geological structure of the crust below Britain. So this is quite a nice example of how geophysical and geological data might complement each other in studying a particular geological problem. Well, so far we've been using measurements of heat determined in boreholes within the continental crust. In the boreholes, the heat flow comes obviously by conduction through solid rock. However, the movement of lithospheric plates around the globe must be accompanied by convective movements of material within the Earth. Plate tectonics is convection because hot magma rises below ocean ridges and cold lithosphere sinks back into the mantle at subduction zones. Well, we can study the geometry of plate tectonics by means of measurements made at the Earth's surface, but to understand the processes of convection within the Earth, we need to make models. If the glycerin in a tank is heated at a point from below, then it begins to rise above that point. This hot material rises to form the ocean ridge, and heat is subsequently lost from the ocean floor during cooling processes. If the glycerin is cooled by using dry ice, then a cold layer forms on the surface and eventually sinks back into the tank. It'll eventually reach the same temperature as the rest of the glycerin in the tank. This models subduction, which happens at active continental margins and below island arcs. So here is our model for convective heat transport within the Earth. We've looked at heat flow in some detail. We've described how it's measured. We've tried to interpret its origin within the crust and mantle. We've concentrated on the Earth's heat because it's the escape of heat from the Earth that's fundamental to all of the Earth's dynamic geological processes.